Swayam Prabha. Digital India. Educated India.
So, you see there is a profound influence of this hydrogen bonding in polymer molecules on the solubility, on the melting behavior, on the mechanical properties, on the processability. So, in case of nylon, in case of cellulose, in case of polyacrylonitrile, that means a polymer, if it contains some polar atoms like oxygen, nitrogen, fluorine, chlorine, halogens, etc. So, that enter into hydrogen bonding and that influences the properties. So, you go through these structures and for new polymers, new other unknown polymers, whether there is hydrogen bonding or not, you can judge yourself looking at the structure. And this diagram shows the change in properties, say volume, say specific volume or relative volume with temperature. And if there is a discontinuity, from the point of discontinuity we can assess a transition temperature, which is known as glass transition, which makes a transition from solid, brittle, glassy state to amorphous, flexible, rubbery state. This occurs due to movement of short segments of polymer chains or segmental movement. This occurs due to onset of segmental movement of polymer chains. For purely amorphous polymers, we get only one transition, which is known as glass transition. For a semi-crystalline polymer, since it contains some crystallites dispersed in amorphous matrix, so one can visualize two types of transitions. One is glass transition and the other is melting transition. In the glass transition, as I said, this glass transition occurs due to segmental mobility, whereas melting transitions occurs due to mobility of the molecule as a whole. In between these, slowly the mobility of the segments increases, and at melting the entire molecule becomes mobile, and so it behaves like a fluid beyond this melting transition temperature. This is another diagram which shows a change of specific heat values of polymers with the increase in temperature or decrease in temperature. You know what is specific heat of a material, of a substance. So, from that definition you can understand, and it shows a change in the slope of this curve, although it is not sharp change. So, gradual change is there. So, in order to get the transition, you have to draw tangent at the 2 points, then at the crossover point of the tangent, that point gives you the glass transition temperature. Then gradually it undergoes a segmental movement, and which helps the crystallization or molecular ordering in the within the system. So, it shows crystallization temperature also, and beyond the crystallization temperature, if the temperature is further increased, then it melts, showing the melting transition. And beyond melting, again you can have certain inflection due to degradation, and those things can be very clear if one analyze a polymer sample through DSC, differential scanning calorimetry, DSC experiment. It basically measures say enthalpy or energy change, may be exothermic or endothermic. This is the temperature axis, and you can get curve like this. Or you can get curve like this, like this. Now, these are actually transitions, again change of enthalpy during the transition, either endothermic transition in these cases or exothermic transition. Now, these transitions can be assigned to glass transition and at lower temperature. That can be a characteristic of one particular polymer, and beyond that again the other transition can be melting transition, where the polymer melts, and beyond that it actually shows degradation, energy change, again it shows the degradation. So, whenever you will be reading the structure your characterization of materials, there you will know the detailed principle of differential scanning calorimetric analysis. There you can know the detail, but this can help knowing the glass transition, knowing the melting transition temperatures, as well as the crystallinity in polymer sample. Because the area under this curve, under this peak, it is proportional to the crystallite, or your if it is crystalline melting, then crystalline melting temperature, then crystallinity can be measured from this area under this curve, or if it is Tg, then you can get this initial, final temperature and the peak temperature. So, you can report these three temperatures or only the peak temperature as Tg. This diagram shows a effect of variation of branch length on the melting characteristics of isotactic poly alpha olefins, say polypropylene suppose, and it shows the properties versus temperature. So, you can explain such behavior of change of mechanical properties with increase in temperature from glassy, solid, brittle state to leathery characteristics to rubbery characteristics to fluid like characteristics. Here you can explain with the help of molecular configurations also what kind of molecular change in molecular configuration occurs. From here you can understand, first of all, on application of stress and mechanical stress as well as heat, what happens, there will be stressing on the bond, chemical bond, as well as that means the energy is applied in two different forms, that helps the deformation of the material, and that will be further augmented or accelerated by increasing the temperature. And this range of temperature between these phases is a glassy range, then beyond that it becomes flexible, then so it is leathery range, and this transition is the Tg from where it passes from glassy to leathery range, then from leathery to rubbery, which becomes little fluid, more fluid than leathery. So, and look at the modulus. Looking at these values, one can know the stress requirement for polymer compounding, for polymer processing, say molding, extrusion, all this, how much stress is required, how much energy will be consumed for such processing. Those things can be understood from these behaviors. This is a kind of phase diagram of these polymer materials, which changes with molecular weight. That means, there is a temperature line above which it remains in one phase, below which it remains in another phase. So, this either it will remain liquid phase or solid phase, amorphous solid phase or crystalline solid phase, that depends on the molecular weight and the temperature. So, up to this molecular weight, say 1000 molecular weight, molecular mass, below this temperature line it is crystalline solid, above it is mobile liquid. Now, if you cross this molecular weight, beyond this molecular weight it becomes viscous liquid. So, viscosity of this fluid is lower than the fluid within this region, and you see it is due to the molecular size. Higher molecular size, bigger molecules becomes viscous in liquid phase, more viscous in liquid phase than the liquid phase, mobility of the liquid phase for discrete molecules. Now, this is the for amorphous materials, this is the line of glass transition, the inter line is the glass transitions. For crystalline material, you see this may be considered as the melting transition line. For glass transition, it can be considered from this initial point to the final point. For crystalline polymers, again the transition line changes, that means it goes up at high, it occurs at higher temperature, because after this beyond this line it becomes liquid, below which it is solid. So, this is the region of tough plastic. Why it is called tough? Now, toughness, if you want to understand the toughness, stress, if you look at the stress strain curve, toughness depends on the stress level as well as the deformation level. So, if you compare this material with another material like this, so say A and this is B. So, B is more tough than A. What does it indicate? That means, it can withstand more stress and absorb energy before failure. So, this will be more, this material will be more resistant to impact load, whereas this will be less resistant to impact load. So, this is tougher than this one. So, this toughness depends on the stress level as well as the deformation level. When some impact energy is imposed on a material, suppose if you give a blow, if it can absorb that energy, then it is tough. So, you have seen the dock fenders, those who have gone through ferry service in Kolkata. In the dock there are some tires attached to the dock. When the your vessel touches it touches the tires, so it absorbs the energy. Otherwise, if there is no such tires which cannot absorb energy, the vessel may be damaged. That means, that material is tough, you understand. So, toughness depends on the mobility of the segments, deformation of the segments, deformation of the polymer chains. So, here you see, here this is a Tg, beyond Tg, that means below Tg is brittle for amorphous material, above Tg it is little flexible. So, it can absorb the shock, it can absorb the impact load, and this will continue till their melting transition. Beyond melting transition, that can be mobile liquid, maybe viscous liquid. So, again that is related to molecular weight of the polymer also. So, this shows a picture of behavior of polymers with temperature and their molecular weight. As you go on increasing the molecular weight, that can withstand higher temperature, that can remain dimensionally stable, that can be tougher, tough material, that can behave like a plastic, that can behave like an elastomer. So, you can predict looking at this kind of phase diagram. Now, here are certain glass transition values are shown. If you try to correlate these values, LDP I explained before also, its Tg is quite low, it may be again minus 120 degree, minus 115 degree, like that. Now, Tg, these values are not fixed actually, because it can vary from one batch of polymer to the other batch of polymer, because not all the batches of polymers which are manufactured in industry will contain same molecular weight level and molecular weight distribution. That is why it can vary. So, it is not fixed. If you see some value in some report, in some paper, in some journal, in some book, it may be written minus 115 degree. It is not wrong, but particularly the value reported over there from one experiment which shows that it is this value is minus 115 degree, but you have seen in a book it is minus 125 degree. Both are right. It gives you some general idea that the Tg values of these polymers, different polymers are such. So, if you compare say Tg value of polystyrene, you see it is 100 degree with this LDP minus 125 high. Why? Because polystyrene contains one pendant phenyl ring. So, that makes the polymer, this phenyl ring, bulky phenyl ring makes the polymer rigid. Achha. This is for hydrocarbon plastics. Now, if you look into other polymers say like PVC, polyacrylonitrile, compare these polymers, that means the substituent at the carbon atom, chlorine, nitrile group, CN group, acetate group, alcohol group, acrylate group, ester group, again another substitution methyl acrylate, methyl and acrylate group, methyl and methacrylate group, butyl methacrylate group, you see the variation, you can easily correlate. That means, the substitution on the polymer chain these substitutions alter the glass transition values depending on their bulkiness, on their polarity, etc. That means, if you correlate this thing with cohesive energy density along with this bulkiness, then you can correlate their Tg properties, how the Tg properties are varying. So, look at this methyl acrylate and ethyl acrylate. Methyl acrylate this is methyl acrylate, this is ethyl acrylate. You see, this is methyl group here, this is the difference between these two polymers, ethyl and ethyl, and for that the length of this alkyl group has drastically changed this Tg value from minus 24 to 6 degree. Further, if you compare another polymer, this is PMMA, compare this polymer with this polymer, its Tg value is minus 24, 6 degree, its Tg is 105 degree. So, that change has come from this methyl group. Now, this shows further examples of other polymers, the Tg and Tm melting transition both. Say you go through these are available in the book. You look at the structure, try to understand why their Tg values are differing from each other, why their Tm values are differing from each other. Examples of various polymers, polyparaphenylene, polytetramethylene oxide, polyphenylene ether. If you compare each of them, there is only phenyl ring, there is no aromatic ring, only alkyl chain, methylene groups, oxygen is there. Again, if you compare this polymer with this polymer, oxygen is there, which is flexible, ethyl linkage is flexible in a polymer chain. So, here you see, although because of the presence of methyl ring, methylene group, its Tg is minus 80 degree. When this 4 carbon atoms of these 4 methylene units are replaced by a phenyl ring, keeping this ethyl linkage same, its Tg has been changed to 80 degree, plus 80 degree. So, this way you compare these polymers with their structures and their glass transition and melting transitions. There are many examples here. Now, let us come to the solubility behavior, dissolution behavior of polymers. Already I have devoted some time to explain before you what do we mean by solubility. Now, for solution to take place, the free energy is the driving force in the solution process, which decreases at constant temperature following the equation. That means, a solution can take place or miscibility of two components can take place. Solubility, what do we mean by solubility? If we mix a component A with a component B, we can get a solution, provided A is miscible with B. In these two components, out of these two components, one may be considered as a solvent and the other may be considered as a solute. You can take the example of a simple case of a solution, say sugar in water. Suppose A is sugar, B is water. It forms a homogeneous solution because sugar is miscible with water. Now, if you take A as a polymer 1, B as a polymer 2, B as a polymer 2, then you can get a polymer blend of polymer 1 and polymer 2, provided they are miscible. That means, you can say this polymer blend may be considered as a polymer alloy if both of them are miscible or compatible. So, we can get a new product from two component polymers by mixing one polymer with another polymer, provided they are miscible. We can say that these two component polymers are miscible at entire range of compositions. between 0 to 100 parts by weight. Means this is a pure polymer 1, say P 1, P 2, 0 to 100 and 100 to 0. These are the two pure, and in between you can have 90, 10, 80, 20, 70, 30, 40, 40, 60, 50, 50 like this. So, in this entire range of compositions, if we see that these component polymers are fully miscible, we can say it is a miscible polymer blend. But it can so happen that one polymer can be miscible with another polymer up to certain specified composition. Say suppose P 1 up to 10 parts by weight can be miscible with P 2 with 90 parts by weight. Beyond 10 parts of P 1, it will separate into phases. That will be a two phase system. That means, there will be some new phase boundaries will be created, one phase of polymer 1 and the another phase of polymer 2. That is, we cannot say that beyond this 10% of P 1 it is not miscible. So, we can say it is an immiscible blend. So, this is the concept, how to know that one polymer will be miscible with another polymer, or one polymer can be dissolved in a solvent, or one solvent can be a good solvent for one polymer and the vice versa. So, that depends on the interaction between a polymer and a solvent, and that can be understood by a solubility parameter delta concept, which is the square root of cohesive energy density CED, cohesive energy density. Delta for non-polar solvents is equal to the square root of heat of evaporation per unit volume, heat of evaporation per unit volume under square root. Okay. And this delta or solubility parameter can be calculated if we know the formula, repeat unit formula of a polymer, if we know the chemical formula of a solvent. So, we can calculate the solubility parameter value of a solvent as well as a polymer. Now, you see heat of mixing of a solute and a solvent is expressed by delta H m, delta H m equal to phi 1 and phi 2 where phi 1 and phi 2 are the volume fractions of polymer 1 and polymer 2, or solute and the solvent. If you consider 1 as the solute and 2 as the solvent, so these are the volume fractions. Okay. And delta 1 and delta 2 are the solubility parameters of the two components, solute and the solvent. This can be two polymers also, polymer 1 and polymer 2. Now, for non-polar solvents, the solubility parameter is also expressed as you have seen earlier, it is the heat of vaporization per unit volume, then delta is equal to delta H v minus R T by V. Replacing this molar volume, replacing molar volume V by the ratio m by d, we get this relation, simple derivation, we get this relation, okay, where d is the density, m is the molecular weight, and delta H v is the heat of vaporization, R is the gas constant, T is the temperature in Kelvin, and m is the molecular weight of the repeat unit of the polymer. Now, since this delta solubility parameter relates with this heat of vaporization, if you correlate this with the intermolecular interactions or interactions between the solvent and the solute or even the solvent, during the evaporation or during the boiling of solvent, what happens? If the energy supplied to the solvent is crosses beyond the intermolecular forces of interaction, then only it starts vaporization, start boiling, vapor formation. Okay. So, it is very much related to the heat of vaporization, which is related to the cohesive energy density, and I told you what is cohesive energy density earlier. Now, look at these values: characteristics of typical primary valence bonds, bond length, bond distance and bond dissociation energies. Of course, these bond dissociation energies has nothing to do with the vaporization of the molecules in which these bonds are present. What I mean to say, if you think of the energy for van der Waals bonds or hydrogen bonds, which is around 2 to below 5 kilocalories per mole. Okay. If the solvation energy goes beyond 5 kilocalories per mole, then only it can break those hydrogen bonds. Do you understand? Take the example of cellulose. Last day I told cellulose contains extensive hydrogen bonding. Almost all the hydroxyl groups in anhydroglucose ring are involved in intermolecular hydrogen bonding. It is a thermoplastic polymer. When it is put in water, it is supposed to go into solution, but the solvation energy of water at room temperature is not sufficient enough to break those hydrogen bonds. But if you add other chemicals, then that chemical energy would cross that hydrogen bond energy and that breaks, and then only cellulose goes into solution. Exploiting this phenomena, technologies have been developed to manufacture processed cotton, mercerized cotton, cellophane, viscose rayon or other regenerated cellulose fibers. Okay. So, this is done by breaking of the hydrogen bonds only with the help of chemical energy. So, but actually these strong bonds again, that depends on the position of the atoms in the periodic table. If there is a more distance between the atoms in the periodic table, the energy becomes more, polarity increases, so energy becomes more. So, bond energy becomes more. So, this way you can correlate looking at these values. Now, look at this data, cohesive energy density, which was calculated or sometimes experimentally determined for these different polymers. You see, for polyethylene cohesive energy density is 56 to 64, for polystyrene it is higher, again for polyisobutylene it is lower than this value, natural rubber is almost comparable, polyvinyl acetate it is little higher, polyvinyl chloride little higher, polymethyl methacrylate still higher, polyethylene terephthalate still higher. This way, if you go on move from polyethylene to different other polymers, and if you look into the structures and their configurations and the atoms present over there, then you can correlate their cohesive energy density. Cohesive energy density is a sum total of secondary valence force, sum total of secondary valence force or secondary valence energy, valence force energy related to that energy related to the secondary valence force, total quantity per mole, of course, per mole, per gram mole or per mole. Okay. Here it is shown per cc, calories per cc, energy consumed or required to break those secondary bond forces are like this, 56 to 64 calories per cc. Okay. You can calculate in terms of mole basis. As I was telling, solubility parameter can be calculated from this relation delta is equal to d into sum of molar attraction constants, and these molar attraction constants are nothing but the measure these are used as for the measure of the cohesive energy density, G values, calories per cc square root per mole, and m is the molecular weight, and this G can be calculated, because it has been evaluated that these G values, molar attraction constants known as moles molar attraction constants, measured by some experiments at 25 degree Celsius. For if there is a methyl group, its contribution is 214, for methylene group it is 133, for CH connected to other 3 bonds it is 28, for carbon attached to 4 different atoms it is minus 93, for CH2 attached to a double bond it is 190. So, you can correlate this thing with the bond energies. That means, these value, if these values are available, suppose if you take a polymer, say this polymer, and you are asked to calculate these G values. So, contribution due to this CH2 group is there. So, here in this polymer in per repeat unit there are 2 CH2 groups. So, you can have this total value for this repeat 2 into 133. In the previous formula you see sum of G values, here you write this 2 into 133 for G is equal to 2 into 133. You can have a molecule or repeat unit formula like this. Here you have to have the contribution from CH2, you have to have the contribution from CH, that means like this. You have to have the contribution from this, you have to have the contribution from oxygen, or you have to have the contribution from OCH3. All these contributions for different groups present in a molecule in the repeat unit formula, and if these data are available for different, you see it is only a few examples are given here, shown over here. In the data book, say there is a data book is a huge data book available in the library known as Polymer handbook. Editors are I. Margut and J. J. J Brandrup, so far I remember Brandrup, you look at that value, you will get several physical constants for polymers, these molar attraction constants, there are Tg values of different polymers, Tm values of different polymers, many physical data you can get from those books. There you can get the small molar attraction constants, exhaustive list of molar attraction contribution to molar attraction constants in chemical compounds. That may be a simple solvent, that may be a polymer molecule. So, with the help of those data available in data book, you can calculate the solubility parameter either for a solvent or for a polymer. Okay. Now, you will ask, sir, what is the necessity of calculating solubility parameter? Is there any necessity? Yes, there is a necessity. If you deal with polymer, suppose you want to do some work on application of polymers, you want to make a biomedical device, say for drug delivery device made of polymer, you want to make a conducting polymer film for sensing purpose, okay. You want to make a surface coating using a polymer. So, for all these you have to go through some processing steps involving solvents, say solution processing or melt processing. Now, if you go for solution processing, then you have to go for selection of a suitable solvent. It is unknown to you, but being a polymer scientist, if you know that this is this polymer, if you know the repeat unit formula of that polymer, then you can easily calculate the solubility parameter of that particular polymer from this equation, from this relation. You calculate the solubility parameter for the polymer, then you see what solvent should be suitable for dissolution of this polymer, or what would be a good solvent for this polymer. How to judge then? Now, if the solubility parameter of a polymer and a solvent are very close, say if the difference is say 0 to 1 to 2.5, the difference in solubility parameter is 1 to 2.5, then that can be measurable. If the solubility parameter is almost identical, then that solvent may be a good solvent for that polymer. So, if you know the solubility parameter value, suppose it is 10 solubility parameter delta value for your polymer, it is 10, then you should find out a solvent whose solubility parameter is close to 10 or 10, say 10.5 or 11 or 11.5 or even 12. So, if you find a solvent whose solubility parameter is close to this 10, then you can select that solvent. It is again not always true that that solvent can dissolve, or the solubility of that polymer cannot be may not be very high in that solvent, but it can be used as a solvent. Say you can easily dissolve 1 gram of polymer in 100 gram of solvent, but you may not be able to dissolve 5 gram of the same polymer in the same solvent, 100 gram of the same solvent. You understand? So, 1 gram is soluble, but 5 gram is not soluble. So, that depends on the solubility limit what is the solubility value. Okay. Look at the data. So, from these molar attraction constants you can calculate the solubility parameter. Look at the solubility parameter values which was calculated or experimentally determined values. For hydrogen it is 3, for dimethyl siloxane it is 5.5, difluoro-dichloromethane 5.5, ethane 6.0. Okay. These are for poorly hydrogen bonded solvents, carbon tetrachloride, propyl benzene, decalin hydrocarbon solvent, xylene aromatic hydrocarbon solvent, benzene aromatic hydrocarbon solvent, styrene structure is different from that of benzene, tetraline, chlorobenzene. So, these solvents are considered as solvents whose hydrogen bonding effect is minimum, poorly hydrogen bonded solvents. Now, the boiling point of a solvent would be high if the molecules in that solvent have very strong hydrogen bonding. So, you look into these values, solubility parameters of moderately hydrogen bonded solvents. So, solubility parameter values increasing in these solvents. Then you see for solubility parameter of strongly hydrogen bonded solvents, earlier I told you a statement that like dissolves like. That means, the chemical nature of the two solvents are equal, or the two components are close chemical nature, say solute and the solvent, then they can be miscible and one can act as the solvent for the other, and that can be calculated or from the molecular point of view, from the chemical nature point of view, one can see in terms of cohesive energy density or solubility parameter values. So, you have seen the solubility parameter values of poorly hydrogen bonded solvents, moderately hydrogen bonded solvents and strongly hydrogen bonded solvents. Now, we come to the polymer side. If your polymer contains strong hydrogen bonding, strong intermolecular hydrogen bondings, so you have to take strongly hydrogen bonded solvents then for its dissolution as its solvent. So, look into the polymer solubility parameter values for polymers. Polytetrafluoroethylene 5 point, again you see it shows different values for poorly hydrogen bonded, moderately hydrogen bonded and strongly hydrogen bonded solvents. So, ester gum, it is a polymer. What is ester gum? Ester gum is a resin made from terephthalic acid and phthalic anhydride or terephthalic acid or and some glycol, using some oils also in combination with oil. So, the ester gum, because those are ester like polymers. So, ester gum and alkyd resins with soybean oils, silicone polymer, polyvinyl ether, polybutyl acrylate, polybutyl methacrylate, you see that their solubility parameter values are lying in the ranges from 7 to 10 like this for these polymers. I will come to explain later. It should be silicone, not silicon, silicone, CONE, silicone. Silicone dimethyl polysiloxane, silicone polymer. Silicone is one grade, polyisobutylene, polyethylene is a trade name of a polymer, polyvinyl butyl ether, natural rubber, hypalon, which is chlorosulfonated polyethylene, and then other polymers, ethyl cellulose, chlorinated rubber, damer gum, that again versamide, trade name, polystyrene, polyvinyl acetate, polyvinyl chloride, phenolic resin, nitrile rubber, PMMA, carbo wax, polyethylene oxide, polycarbonate, cyclized rubber. These are the values. Solubility parameter values for polymers, again mylar in the form of film, mylar film, polyethylene terephthalate film, vinyl chloride, vinyl acetate copolymer, polyurethane, styrene acrylate copolymer, shellac, cellulose. So, you see here from these data, if you know the solubility parameter delta for a polymer, say suppose it is 11, then you look at the solubility parameter of a solvent, go to the solvent chart. Here you see there are solvents whose solubility parameters are 11.4, 11.5, 12, 10.9, 10.6, 10.3, and go to the polymer chart. See this polymer, you take a polar polymer, say alkyd resin, or this no, it will be little complicated. You take natural rubber, example of natural rubber. Natural rubber, its solubility parameter is around say 8.5, okay, and its solvent for natural, good solvent for natural rubber is benzene, xylene, toluene. These are the solvents, hydrocarbon solvents. Decalene, tetraline, these are also good solvent for natural rubber. So, if you put natural rubber in benzene, it will go into solution. So, look at the solubility parameter values of benzene and benzene, toluene, xylene. (9.2) for benzene it is 9.2. So, difference is 9.2 minus 8.5, it is very close. So, if the solubility parameter values of the two polymers are close, then we can consider that these polymers, this solvent, this particular solvent can be used as a very good solvent. So, this way you can go for selection of solvent for a suitable polymer. So, if there is any question on this thing, you ask me, any doubt? Any question? The structure, properties, relations of polymers.
energy is not directly related to PD. The bond energy of the chemicals.
But bond energy is related to the cohesive energy density.
It is related.
Of course,
But sir, in
you
CD,
take the example of polyethylene and polyethylene terephthalate. Or nylon. In nylon there is hydrogen bond in addition to van der Waals forces, say London dispersion force, and this hydrogen bond is present due to the presence of nitrogen and oxygen, NHCO, amide linkage. That so this polar interaction is there. So, due to polar interaction, these hydrogen bonds are coming into picture. In case of polyethylene, no polar interaction, only it is London dispersion force. Where from it is coming? It is coming from the bonding electrons, induced effect of bonding electrons. Okay. So, that is the cohesive energy density of polyethylene. In case of nylon, cohesive energy density is a contribution from polar bond as well as non-polar bonds. Okay. That is why nylon is soluble in acid. It needs a strong solvent. It can be dissolved in say dimethyl formamide or dimethyl acetamide or dimethyl sulfoxide. These are highly polar solvents. So, highly polar solvents can dissolve this polar polymer. Even there are some polymers like polyimides, sometimes cresols, metacresols, paracresols, phenols, concentrated sulfuric acid, these are used as solvent for those polymers. You understand? Whereas, these common solvents cannot dissolve them. Tetrahydrofuran is a good solvent for polyphenol chloride. What is the solvent for polyphenol alcohol? Water. This is a water soluble polymer. Okay. But hydrocarbon solvents cannot dissolve this polyphenol alcohol. Polyethylene, for polyethylene, although this hydrocarbon solvents can be a good solvent, but it does not dissolve at room temperature. You have to break the crystallites. So, for LDP, toluene is a good solvent at its boiling temperature. For HDP, xylene is a good solvent for HDP. Xylene is a good solvent. So, you please go through these slides I have told, you have taken some notes and then read some books, complete the note and try to understand. Thank you.